In this video, we are going to talk about change of bases, which is another way of saying given a vector, we are going to convert a vector's coordinates with respect to a basis B to coordinates with respect to a basis C. Since we are talking about changing coordinates, we should review the definition of a coordinate. So if we have a vector space V and a basis for that vector space, the basis is B and it's equal to the vectors V1, V2 through Vn. Then for each vector W in the vector space, there's a unique set of scalars, W1, W2, Wn, such that W is equal to W1 times vector basis vector 1 plus W2 times basis vector 2 all the way up to Wn times basis vector Wn. In other words, these W1, W2, Wn, those are the scalar multiples, the things that multiply our basis vector so that when we take this linear combination, we get our vector W. So these scalar multiples are the coordinates of W with respect to B. And notice also there is an order to them, right? Because you can't just swap the scalars around. But as you know, for any given vector space, there may be more than one basis. So if we have two bases B and C for the same vector space, we want to be able to convert from coordinates of one basis to coordinates of a second basis. And we can do this with a matrix P, which is n by n. And it's n by n because both of these bases have to be the same dimension since they represent the same space. So an n by n matrix P, where the first column, so if we're converting from basis B to basis C, the first column is going to be P sub 1, which is U1, the coordinates of U1 with respect to basis C. And then etc. So P sub I is the ith basis vector of B expressed in coordinates with respect to C. And we'll do this example to clear things up. We have the example, let B and C be a basis for P2, the space of polynomials of degree 2 or less. And we have B is our first basis, 1x, x squared. This is our natural basis, and I'll talk about that more in just a minute. Our second basis is 1, x plus 1, and x plus 1 squared. We want to find our transition matrix P such that when we plug in for a vector Q, its coordinates with respect to B, we are outputting, after multiplying by the matrix, its coordinates with respect to C. In an earlier video, I had talked about P2 being a vector space, and I kind of outlined that we could prove that, we would prove the properties of vector space such as closure, addition of two polynomials of degree 2 or less is still a polynomial of degree 2 or less, which of course you know. Closure is scalar multiplication. You multiply a polynomial by a scalar and it's still a polynomial of degree 2 or less. Addition is commutative. When you add two polynomials, it doesn't matter which one you add, you make your first polynomial versus your second. 0 is the additive identity, and you can go through all of the properties and show that P2 is a vector space. And we also showed that B equals 1x and x squared is a basis because you can write any polynomial as a linear combination, so A, B, and C are my scalars, of 1x and x squared. The other thing I'm going to mention, B is our natural basis for a polynomial because the coordinates come out naturally as A, B, and C. It's much like, and I'm just going to write this in blue, it's much like for two dimensions, 1, 0 and 0, 1 is our natural basis. In the same way, 1x and x squared is a natural basis for polynomials of degree 2 or less. Now going back to solve this problem, I want to write our bases and our vectors in terms of the notation we have in our theorem, just so that it kind of falls out more naturally. So in terms of our theorem, our first basis vector with respect to B is equal to U1. Our second basis vector is x, that's U2, and our last basis vector is x squared, which is U3. And I want to find a matrix P that'll then translate the coordinates with respect to B to coordinates with respect to C. So what I need to find, where is that? My ith column, so my first column, P1, is going to equal to my first basis vector with respect to B. So that's U1. I need to find the coordinates with respect to C. P2, I'm going to find the coordinates of my second basis vector with respect to C, and P3 is the coordinates of my third basis vector with respect to C. So for 1, our first basis vector, I want its coordinates with respect to basis C. So I want to write 1 as a linear combination of the bases of C. So I have 1 is equal to some scalar A times 1 plus some scalar B times my second basis vector, which is x plus 1, plus some scalar C times my last basis vector, x plus 1 squared. Well, looking at 1, that means that A1 is equal to 1 and B and C can be equal to 0. So my coordinates for 1 in this basis is 1, 0, 0. For P2, now I want to write my second basis vector x in terms of my new bases. So I want A times 1 plus a scalar B times x plus 1 plus a scalar C times x plus 1 squared. And that algebraically gives me A plus bx plus B plus cx squared plus c times 2x plus c. And again, I just want an x. So that means my A, B, and C, since I have no constant term, is going to be 0. My coefficients of my x term is B plus 2C, and that's going to equal to 1 because I want x, my coefficient in front of x to be 1. And then my x squared, well, there's no x squared term, so C is going to be equal to 0. So what that gives me is B is equal to 1 and A is equal to negative 1. So x is equal to negative 1, 1, 0 times, that would be my coordinate with respect to the basis C. And you can check this by writing A, that's my first coordinate, negative 1 times my first basis, 1. B, which is 1, times my second basis vector, x plus 1, plus the C here, 0, times my x plus 1 squared. And when you do this multiplication out, you're going to be left with x. Last, I want my last basis vector, x squared, in terms of my new bases. So I have A times 1, B times x plus 1, plus c times x plus 1 squared. Algebraically, and you can check my algebra, c is equal to 1, b is equal to negative 2, and a is equal to 1. So my coordinate is equal to 1, negative 2, 1. And I should put my bases here with respect to c. I kind of shrank my work down so I would have room for my final answer. So now p is equal to p1, which is 1, 0, 0, p2, which is negative 1, 1, 0, and P3, which is 1, negative 2, 1. This is my transition matrix. Now with my matrix here, I can convert any polynomial of degree 2 or less to coordinates with respect to my basis C. And first, I take my polynomial and I convert it to my basis B, the natural basis, so that makes it quite easy, 2, 3, and 1. Now I can multiply P times my 2, 3, 1, and I get, after I multiply this matrix out, 0, 1, 1. And you can verify that 0 times the first basis vector in C, 0 times 1, plus 1 times the second basis vector in C, so that's 1 times x plus 1, plus 1 times the third basis vector, x plus 1 squared. When you multiply this out, you will get x squared plus 3x plus 2. To review what we have done in this video, we did a change of bases, which is another way of saying we convert a vector's coordinates with respect to B to coordinates with respect to C. The first thing we did is reviewed what it was to be a coordinate. So for a vector W in V with a basis B, which is V, V1, V2, up to Vn, the coordinates of W are simply the scalar multiples we use in front of our basis vectors in order to have a linear combination equal to W. Then for our change of bases theorem, we can, if we have two bases for the same vector space, so we have a basis B and a vector C, a basis C, sorry, not a vector, but a basis C, then if we want to convert from coordinates in B to coordinates in C, we can generate this matrix P. And what we do for each column vector is our ith column vector is equal to our ith basis vector in B, written as coordinates with respect to C. And we did this example here. So for the vector space of polynomials of degree 2 or less, we had two coordinate systems, two bases, One was 1x and x squared, and then our second basis was 1x plus 1, x plus 1 squared. In order to find our first column of our matrix P, to convert from coordinate system B to C, our P1 was equal to our first basis vector, which was 1, written as coordinates with respect to C. So 1 was equal to 1, 0, 0 with respect to C. P2 then was the column vector of coordinates of x, our second basis vector, with respect to C. So we wrote x as a linear combination of the basis vectors of C, 1, x plus 1, and x plus 1 squared. And we found that the coordinates would have to be negative 1, 1, 0. And then finally, we took our last basis vector x squared, wrote it as a linear combination of the basis vector in C, and we found the coordinates would be equal to 1, negative 2, 1. And our final matrix was then just these column vectors here, these three column vectors into the matrix. So that's it for this video. Thank you for watching.